Hello viewers, welcome to my YouTube channel VK Civil Hub. I am Professor Vinod Kumar, Department of Civil Engineering, and I request you to watch the video till end so that if you have any doubts you can give in the comment section or you can contact me through my mail vinodkucivil@gmail.com. Let's get into the video. In today's video, we are going to see the fundamentals of stresses and strains. Before that, let's have a small introduction on the forces acting on the body. Here you can see in the diagram, a body is considered and a force P is given in the first part of the body. Let's consider a section XX in this body so that the cut section is shown in the second part. Now here comes the main point. What happens when a force is given to a body? There is a resisting force created inside the body that is shown in the second diagram. Here is where the Newton's third law is applied. For every action there is an equal and opposite reaction. So for this force P, there is an equal and opposite reaction R. So here this R is equal to P. P is your given load, R is your resisting force, and A is your area of cross section. So when the applied force P acts on the body, it produces some deformation in the body. That is, the body shape gets changed. And there is a resistance force R also set up within the body. Now when this P is equal to R, that is when the applied force is equal to the resistance force, the deformation stops. What happens when this applied force is greater than the resistance force? Ultimately there will be a failure taking place at that place. This deformation in the body is referred by the terms stress and strain. Now let us see what is stress. Stress is actually defined as the internal resistance R per unit area A. We have seen both these things in the diagram. This stress is measured in Newton per meter square in SI units, and it is specifically called Pascal, denoted by PA. A bigger unit of stress is the megapascal MPa and gigapascal GPa. Mega is 10 power 6 and giga is 10 power 9. So this stress sigma, denoted by sigma, is equal to the resisting force by the area. Now we know that R is equal to P. So the stress formula becomes sigma is equal to P by A Newton per meter square. Now let us see the conversion of megapascal into Newton per mm square. Why do we want to do this? Because these values are same. That is 1 megapascal is equal to 1 Newton per mm square. That is what I am going to explain now. We know that 1 Pascal is equal to 1 Newton per meter square. That is the unit of stress. Now what happens to 1 megapascal? So 1 mega is equal to 10 power 6. This becomes 10 power 6 Newton per meter square. Now in the denominator there is a meter. We have to convert it into mm. So what happens to that? 1 meter is equal to 1000 mm. That is 10 power 3 mm. If you whole square that, you will get 10 power 6 mm square. So in the numerator there is a 10 power 6. Denominator there is a 10 power 6. Both these gets cancelled and you will get 1 Newton per mm square. That is, the value of 1 megapascal is equal to 1 Newton per mm square. These units will be given in the book, so both are same. That is why this conversion is explained. Now let us see the types of stresses. There are three main types of stresses. One is the tensile stress. Here you can see in the diagram, the force acting is away from the body, so we call it as tensile force. So the stress formula sigma is equal to P by A becomes sigma T is equal to P by A, where T refers your tensile load. Due to this tensile load, the bar gets elongated, that is, it gets increased. The second one is compressive stress. Here you can see in the diagram, the force acting on the body is towards the body, so we call it as compressive force, and hence the sigma is equal to P by A becomes sigma C is equal to P by A, where C refers the compressive force. Due to this compressive force, the bar gets contracted, that is, it gets shortened. The third one is shear stress. You can see in this diagram, two bars are attached with a rivet. The yellow color one is your rivet. What happens when a force is given to this body? the rivet gets a cut. So the stress formula becomes tau is equal to P by A, where your tau refers to your shear stress. Due to this shear, the rivet gets a break. Apart from these three main stresses, there are also other stresses which are normal or direct stress. That is, when the stress is acting perpendicular to the plane of the section. Simple or pure stresses. When the stress induced in the body is single, we call it as pure or simple. The third one is volumetric stress. Here you can see in the diagram, the force or load P is acting on all the directions, that is X, Y and Z directions. So due to all the three forces, the stresses induced in all three directions, we call it as volumetric stress. There will be a change in the volume of the body. Now let us see what is strain. Strain is actually defined as the ratio of change in dimension to its original dimension. When we consider a body, there will be length, breadth or depth or diameter. Whenever this dimension changes, when we compare to the original dimension, the ratio between these two, we call it as strain. Since both the dimension on numerator and denominator are same, it is a dimensionless quantity and it doesn't have any units. What are the different types of strains? There are three different strains. One is the linear strain, another one is lateral strain, another one is volumetric strain. Now let us see linear strain. Linear strain is referred with the length of the body. So linear strain is equal to the change in length by original length of the body. So this strain denoted by E is equal to delta L by L, where delta L is your change in length and L is your original length. Here you can see in the diagram, the first diagram shows a body with length L and a tensile load is acting on that body. So due to this tensile load, the bar gets extended and that particular strain we call it as tensile strain. In the second part, the load is a compressive load and the actual length of the body gets decreased with a delta L. So that particular strain is called compressive strain. Next, lateral strain. Lateral strain is along the other two dimensions apart from the length. So lateral strain can be change in breadth by original breadth if breadth is taken as the consideration. So your strain formula E is equal to delta B by B, where delta B is your change in breadth and B is your original breadth. If we consider depth as the point, lateral strain becomes change in depth by original depth. So your E becomes delta D by D, where delta D is your change in depth and D is your original depth of the body. Next we will see volumetric strain. Volumetric strain is equal to change in volume by original volume. Here we take the volume of the whole body. So your strain formula becomes EV is equal to delta V by V, where delta V is your change in volume and V is your original volume. Here you can consider the body with dimensions length, breadth and depth along the all three directions. So here the volume, we know that it is the product of length, breadth and depth. So V is equal to LBD. Next, delta V, that is change in volume. We are having three dimensions L, B and D. So while considering the change in dimension for the length, it becomes delta L and the product of B and D. We have to separate all these three terms. Then next, breadth is taken as the consideration. So it becomes delta B into product of the other two dimensions L and D. The third part is delta D into L into B, while depth is taken as the consideration. So the summation of all these three things will give you the change in volume delta V. Now what happens if these both are divided? that is we get delta V by V, that is the volumetric strain. So what happens? Delta L into BD divided by LBD gives you delta L by L. Similarly, for the second part we get delta B by B, and for the third part we get delta D by D. So this volumetric strain is delta L by L plus delta B by B plus delta D by D, that is strain along x direction plus strain along y direction plus strain along z direction. Now let us see what is shear strain. Here in this diagram given, it is a cube ABCD. AB is fixed and the DC is free. So for this body, what happens when we give a shear force P, that is the force acting along the surface of the body. The body shape gets changed as shown in the diagram with dotted lines, and it refers A, B, C dash, D dash. It is like a rhombus. So what happens? The DC is moved to D dash, C dash, and that C dash extended length is your delta L, that is change in length. So here the shear strain becomes change in length by original length, that is C dash divided by the original length is CD, that becomes C dash by BC, because CD is equal to BC also. So from this triangle we get the shear strain as 5 radians. Okay, till now we have seen what is stress and its types, what is strain and its types. Now we are going to see what is the relationship between this stress and the strain. Actually, this relationship is based on the elastic behavior of materials. Here we are taking mild steel as an example, and that particular steel is given a gradually increasing pull, that is a tensile load. This is done in a universal testing machine, which we call as UTM in short. The stress strain curve obtained as a result is shown below. Here in this diagram you can note stress is along the y-axis, strain is along the x-axis, and O is your origin point. From O till A you can note it is a straight line, that is the result is within the elastic limit. So the stress at point A is called as your elastic stress, that is your limit, and beyond that limit the mild steel starts to yield. So at the point B you call it as upper yield stress, and the point C it is getting down, so it is the lower yield stress. Again it's getting increased, and at the point D is where the load, the steel can take maximum load without failure. So that point D is your ultimate stress, and beyond D at the point E the mild steel gets failure, that is breaking. So that E is called as your breaking stress. Now let us see what is elasticity and elastic limit. Elasticity is defined as the property by virtue of which the body regains its original size and shape when the deformation force is removed. That is, the actual size will be there and there is no loss. So the maximum stress up to which the material can exhibit this property of elasticity is called as the elastic limit. In previous diagram I showed you A is your elastic limit. If the deformation exceeds this limit, that is the elastic limit, there will be a permanent set in it. So we call it as plastic stage. That is, the body retains its original shape. Here you have to understand the difference between regain and retain. Regain is getting back to original position, retaining is set in that position, it will not get back to its original position. So here this yield stress, we have already seen the stress beyond the elastic limit. Ultimate stress is the stress at which the material starts to break. Working stress is defined as the ratio between that yield stress and a factor of safety. This factor of safety differs for different materials. Now let us see what is Hooke's law. I already explained that, we'll see later in this chapter. So here in this Hooke's law states that the stress is directly proportional to the strain, and that is up to elastic limit only, that is the point A in the diagram. If sigma is your stress and E is your strain, then according to Hooke's law, this sigma divided by E gives you capital E, that is a constant. If you remove the proportionate symbol, we will get division, and that is equal to a constant. That constant capital E is called as the modulus of elasticity or Young's modulus, both are same. This is named after the English scientist Thomas Young. Next, let us see what are the different elastic constants available. These elastic constants are actually expressed with the relationship between the stresses and the strains. In Hooke's law, I explained you what is Young's modulus. So that is one elastic constant, and that is the ratio between normal stress and normal strain, that is sigma by E. The second one is modulus of rigidity or shear modulus, and it is denoted by G. Here you have to make a note. In some books it will be denoted as C and N, capital C and capital N. Here I have taken capital G as the notation for modulus of rigidity. So this G is equal to tau by phi. We know what is tau, what is strain. It is the ratio between shear stress and shear strain. So this is the definition for modulus of rigidity. Next, bulk modulus denoted by capital K. We have seen volumetric stress, we have seen volumetric strain. The ratio between these two gives you the bulk modulus, that is K is equal to sigma V divided by EV. Next we are going to see is Poisson's ratio. When a body is given a load, it can be either tensile or compressive. What happens if the load is tensile? The length gets increases, and simultaneously the breadth and depth of that bar will decrease. On the other hand, if the load is a compressive load, the length will get decreased and simultaneously the breadth and depth increases. So how we are going to calculate all these strains and stresses while working out the problems? We need this Poisson's ratio. So actually this Poisson's ratio is defined as the ratio between the lateral strain and linear strain. We have seen what these two are before itself. Lateral strain along the other dimensions, linear strain is along the length. So this lateral strain divided by linear strain gives you Poisson's ratio, and it is denoted by 1 by m or mu. Some book uses 1 by m and some other books uses mu. Both are same. This value of Poisson's ratio for most of the materials lies in the range of 0.25 and 0.33. Here also there is no unit because both the values are strain values on the numerator and denominator. We know there are three elastic constants, viz. Capital E, your Young's modulus, capital G, your modulus of rigidity, and capital K, bulk modulus. Now what are the relationship between these three elastic constants? In order to derive the relation, we need this Poisson's ratio mu. So here the relation between Young's modulus and modulus of rigidity is given by E is equal to 2G into 1 plus mu. You can use this relation in the problem. Next comes the relation between this Young's modulus and bulk modulus, capital K. E is equal to 3K into 1 minus 2 mu. Third comes the relation between all these three, E, G and K. It is given by E is equal to 9GK the whole divided by G plus 3K. In some books this modulus of rigidity is denoted as N, C or G. Next we will see bars of uniform section. Here we know that the stress sigma is equal to P by A and the strain E is equal to delta L by L. Let us denote this as equation number 1. From Young's modulus formula, E is equal to stress by strain. We get strain is equal to stress by Young's modulus, that is sigma by E. And if you substitute the value of sigma is equal to P by A here, we get as P by AE. Let us denote this equation as 2. Now equating 1 and 2, we get delta L by L is equal to P by AE. When you cross multiply this, we get the value of delta L is equal to PL by AE. This formula is very important while calculating the problems, because in some problems the strain value will not be given. Without knowing the value of the strain E, you can't find the change in length. So we are using this formula to calculate the change in length delta L as PL by AE. Okay viewers, hope you have watched the video in full. If you have any doubts, you can comment in the comment section, or you can contact me through vinodkucivil@gmail.com. If you really like my video, kindly subscribe to my channel VK Civil Hub for further updates. Thank you.